Welcome back to the tutorial series on sequential decision analytics. This is going to be my first crack at describing the universal modeling framework, but at a high level. So this is going to be sort of a quick tour of the universal modeling framework. We will come back to this a second time, do it at a much more detailed level. So sequential decision problems. We have decisions, information, decisions, information. Any sequential decision problem has this. Now, the way I model a sequential decision problem is at time t, we have what we know or believe. This is called the state variable, but this is the state of knowledge, okay? So you take what you know or believe, then you have the decisions. This is the information that you control, and you make this decision on the basis of what you know or believe. And then there's information coming from outside the system that I don't control. It might be something totally exogenous like weather delays, or it may be somebody else's decision. And then we repeat back and get an updated state variable. Each time we make a decision, we compute performance metrics, and there may be my whole pyramid of metrics. It depends on the state, what I know, and it depends on the decision. Now, I may have metrics that depend on Wt plus 1. If I use this notation, I'll compute that at time t plus 1. Or I can just wait and say, I'm going to have a metrics that depend on the state and the decision and the new information. Doesn't matter. So we have a set of performance metrics. Now, decisions are made with a method that we're going to call a policy. And I'm going to use the notation that if I represent a decision using the variable x, lowercase x, I'm going to represent the method that we make decisions, called a policy, with capital X. Then I'm going to put a superscript Greek letter pi for policy. But my Greek letter pi is different than what people say in computer science do. Computer scientists like to call policy the function. To me, I take the variable pi and I put what type of function. Okay, I actually put the information on what the function looks like. Now, the main thing about the policy is we're going to design this later. And this is a really key point because this differs from all of the other communities where if you go back to my Jungle of Stochastic Optimization, which has all these various books, including mine, all of them focus on a method. They're all out to say, hey, here's a method for making decisions. In my framework here, I'm just going to give you some function and say, I'll get to that later. I don't know what it is. I'm just going to give it a variable name and, to be designed later. Now, once we say that we have some function that I haven't designed yet, we're going to have something called a transition function. Now, this notation, the concept of transition function comes from the community called optimal control. My notation is different. I don't use little f for the function because f is a very useful letter in the alphabet. I use s superscript m for the state transition model. And it depends on the state that you're in, what decision that you make, and then what new information comes in. The state transition function then gives you the updated state. This is very practical, easy to compute, assuming that you know the function. Now, the goal is to find the function, the policy, that works the best over time. Okay? So I haven't yet told you what function we're going to use, but at least I've told you the performance metric and the framework of saying, okay, if 5 people can come up to me with different competing functions, I can put it in this objective and see which one works best. So my universal modeling framework is basically sitting in front of you right here on this one PowerPoint slide. Now, I haven't told you how to make decisions. I haven't told you the policy. And there's a lot of details to be filled in. But this one slide is roughly the universal modeling framework. Now, I like to organize the framework into 5 components: the state variables, decision variables, the exogenous information, the transition function, and the objective function. With those 5 elements, I can model any sequential decision problem. Okay? So any of those problems over there on the right, in any of those pictures, or anything in any of these books. So I can take any of these books and translate how they're solving a problem into this notation. I haven't solved the problem, but at least I can write it down. Now, this is the foundation of what I've done in my big book. The Universal Modeling Framework is all contained in Chapter 9, which you can download for free from tinyurl.com/RL&SO. You can also download you can also go, that's where the book webpage is. By the way, this is the only book that you cannot download for free. I'm not allowed to do that, but you can go to Amazon and purchase it. Now, what we've done is in the previous module, I talked about framing the decision problem. Framing the decision problem identified the metrics, identified the decisions, and identified the uncertainties. So those are the three things. No math and no notation, but at least in English I says, here's the metrics that we're going to be trying to optimize, here's the decisions we're trying to make, and here's the forms of uncertainty. Now this also shows what we didn't cover. We didn't cover state variables. We can't get to state variables until I start filling in some other information. So you can download this book for free, or there's an online version on the SDA website, and you can just read for it. It's very nice on the website because you can flick around the website. You can also do searches and that sort of thing. On my to-do list, forthcoming maybe late in 2026, possibly 2027, I'm going to have another monograph. This is going to be an expanded version of Chapter 9 of my big book. So this is going to be all about the 5 elements, nothing about how to make a decision, but it will have all the notation. So if you are interested in doing real-world modeling, this will be a much more advanced modeling book, even than Chapter 9 of my big book. Now, when you make decisions, I'm just going to briefly say there are 4 fundamental classes of policies for making decisions. These are covered in depth in this book. They're also covered in the on the website. I'll come back to this later. Otherwise, I'm not going to say anything more about making decisions. I will be maybe sometime next year coming out with a new monograph where I focus on policies working from the most commonly used to the least commonly used. Now, let me point out, here I've just illustrated a stochastic gradient algorithm. If this is familiar to you, people don't realize this is a sequential decision problem. That alpha n, which is called the step size, that's the decision, okay? And in Chapter 5 of my big book, I show how to model this as a sequential decision problem. Here's the 5 elements from state variables, decision variables, like the step size, the exogenous information, the transition function, and I show those there, and then the objective function. So I model it as a sequential decision problem. This is not widely appreciated, but anytime you have an iterative sequential algorithm, you can write that as a sequential decision problem. Now, if you go back to the classical modeling framework that Marty Putterman uses, this is a screenshot out of his book. So he has decision epochs, that's just his time variable, state variables, actions, rewards, and the transition probability. He has rewards, but no objective function, which is very interesting. Compare that to my universal modeling framework. So my universal modeling framework, I'm going to argue, is both more general. My state variable recognizes physical, informational, and belief variables. The transition function is always computable. Whereas the transition matrix is not. But notice number 5, that's the objective function where I search over policies. And this is actually a very important dimension of writing out objective functions that's often missed. For example, if you go to the Princeton reinforcement learning course, they write up the objective function. Notice that they're not optimizing over anything. They have utterly left that out. So they should have an expectation out front, but they need to be searching over policies, and they don't seem to recognize that. The dynamics they assume is represented by a one-step transition matrix, again, not computable. So this is a sharp contrast between how I write sequential decision problems and how it's written, for example, in reinforcement learning. Now, one thing that they like to emphasize, both the reward function and the dynamics function are unknown. This is a standard assumption in computer science. They like to say, oh, but we don't know the reward function, and we don't even know the dynamics. This is very odd, but what they're doing is they're going back to the days of Pavlov's dog, where they don't know the reward function of the dog or the animal or even a human making decisions. And when it's out there in the field, they don't actually have the mathematical model of the dynamics of how things evolve over time. In practice, people do know the reward function like a chess game. They do know the dynamics like a chess game. And there are people who say that they're doing reinforcement learning, and they will define reinforcement learning as what's going on inside a simulator, which means You know the reward function and you know the dynamics because you're simulating them. So there's a lot of confusion in this community on this. Now, they also say the policy, first, what's right there in the document is this doesn't say anything about where the actions come from. Well, it comes from a policy, which is some function. And then what is the optimization problem over? Well, that's the important question, but then they don't even talk about what the optimization is over. The answer to that question is they're optimizing over policies, and they need the 4 classes of policies. What happens here in the Princeton course is they just jump to saying, well, we introduced the policy, which is a distribution over actions, which again, most of the time it's not a distribution over actions. So again, a lot of confusion here. Once again, this is my very high-level overview of the Universal Modeling Framework. If you go to the warrenpowell.org website, click on modeling. There's a whole section called the Universal Modeling Framework. And then if you go to the teaching materials and books, there are 2 books, Sequential Decision Analytics and Modeling, which is available online. And then there's chapter 9 of my big book, which is also, the PDF for that is can be downloaded for free.